Can a linear regression be used to model a nonlinear relationship between a response variable and an explanatory variable? Many people are under the misapprehension that linear regression models can only be used to model linear relationships between a response and an explanatory variable. But this couldn't be further from the truth. Linear regression models can be used to model highly nonlinear relationships between a response variable and one or more explanatory variables. Their misapprehension results from a misunderstanding of the meaning of the word linear in the names linear regression and linear model. A regression model is said to be linear if its deterministic component is a linear function of the parameters. It has nothing to do with the explanatory variables. So even if the deterministic component of the model is a nonlinear function of the explanatory variables, if it's linear in its parameters, it is a linear model. This means that the statistical procedures for linear regression can be applied to any linear regression model, even if the relationship between the response variable and the explanatory variables are highly nonlinear. I'm going to demonstrate this and show that it is true even for the most basic type of linear regression model, the simple linear regression model. We'll do this in the context of a simple example with a small data set so that we can focus on the overarching concepts. We'll see that the estimation procedures we have been looking at for simple linear regression models will be applicable in this situation as well. So let's take a look. So here is the data set that we'll be using for this example. It contains 10 observations. The response variable is labeled y, and the explanatory variable is labeled x. And so the first question I have for you is, can you detect from visual inspection of the data set anything in the data? Can you determine any kind of relationships that exist between the two variables? For example, are you able to discern whether there is an increasing or decreasing relationship between x and y? Are you able to determine whether the relationship is linear or curvilinear? In most cases, it's difficult to ascertain, much by just looking at the raw data. To answer these questions, the data need to be subjected to various forms and levels of statistical processing. Now, by forms, I mean graphical techniques, organizational techniques, numerical techniques. And by levels, I mean various levels of complexity, starting with perhaps simple summaries and progressing to more complex approaches such as modeling and hypothesis testing. Now, a good first step when evaluating the relationship between two variables is to create a scatter plot of the data. I've created one, and we're going to see that on the very next slide. So here is a scatter plot of the data set. We have the response variable y on the vertical axis and the explanatory variable x on the horizontal axis. And so the first question I have for you is, does this scatter plot appear to be linear, or does there appear to be some curvature to it? Now, to help see that, we can go ahead and superimpose a straight line through the data, and the model for that line is of the form y equal to beta 0 plus beta 1 times x plus epsilon. And with that line superimposed over the data, there does appear to be curvature in the data set. And so perhaps a quadratic term would capture the nonlinearity better. And so instead of having x in the deterministic part of the model, we could have x squared. And the curve we have here is a model of this form. And I think you would agree that that does appear to fit the data much better. So with this in mind, let's add a derived variable to the data set, and let's call it w, and it'll be equal to x squared. And so I've added a column for the derived variable, and you can see here that that second column, w, which is equal to x squared, does in fact have the squared values of x. So for example, 0.2 squared is 0.04, 0.3 squared is 0.09, and so forth. Okay, next, let's create a scatter plot of y versus the derived variable w, which again is equal to x squared. And so now we have a scatter plot with, again, y on the vertical axis, but instead of having x on the horizontal axis, we've got w, or x squared. And so the question is, does this scatter plot look linear? Well, I think that looks a whole lot linear than the first scatter plot, but let's go ahead and superimpose a straight line through that data set. And even with that straight line through it, I don't really detect any curvature, any quadratic trend or even higher term. And so that looks like it fits pretty well. And so what can we tell from these scatter plots? Well, I think we can tell that first, y is quadratic in x. Also, y is linear in x squared. All right, so what I want to do next is use the procedures that we've used in the course up to this point to fit a quadratic relationship between the response variable y and the explanatory variable x. And we're going to do this first using a visual fitting process like we did in a previous lecture video. So we're going to be doing a visual fitting of a quadratic relationship using a simple linear regression model. So let's take a look at this spreadsheet that I've created for visually fitting simple linear regression models. We're going to be fitting a quadratic trend using a simple linear regression model. The first thing I want to point out is that I have the data set in two places in this spreadsheet. In the upper left corner, I have the data set where I'm using x as the explanatory variable. In the top right, I have a version of the data set where I'm using w equal to x squared as the explanatory variable. Now, for each of those data sets, using each of those two variables as the explanatory variable, I have predicted values, y hat. So you can see that in both those spreadsheets. And then I also have a column for the square of the difference between the observed value of y and the predicted value of y. All right, and so you can see that I have those two columns, the predicted values and the square of the difference between the observed value and the predicted values in both columns. And then I total up that last column in each spreadsheet, and that gives me the sum of squares error, the SSE, for each of those representations. Now below each of the data sets, I have a graph where I've created a scatter plot of the data for the respective data sets. And so in the graph on the lower left, I have a scatter plot of the data, and I have y on the vertical axis, that's the response variable, and on the horizontal axis I have x. On the lower right portion of the spreadsheet, I have a graph, scatter plot of the data set up above, where w is the explanatory variable, w again being x squared. And then above the graphs I have the corresponding models that I'm going to be fitting. So above the graph on the lower left, all right, I have y equal to beta 0 plus beta 1 times x squared plus epsilon. And above the graph on the lower right, I have y equal to beta 0 plus beta 1 times w plus epsilon. Now, this is the canonical representation because I've replaced the x squared term with w. And if you look at these two graphs, in the lower left corner, where x is the explanatory variable, we can see curvature in that scatter plot. All right, and so it's pretty clear that there's a nonlinear relationship between the deterministic component of the model, in other words, the expected value of y, and the explanatory variable x. On the other hand, in the scatter plot where w equal to x squared is the explanatory variable, that scatter plot looks linear. Now, what I want to do is to adjust the parameters beta 0, which is the y-intercept, and beta 1, which is the coefficient multiplied against x squared in the model on the left and w in the model on the right. I want to adjust those values and see if we can get this function that is displayed in green to better fit both of these scatter plots. Now, both of these functions are tied to the box in the middle with those parameter estimates. And in the left-hand graph, that green function, which is linear now, but you'll see that it is actually, it has this form here, y equal to beta 0 plus beta 1 times x squared, all right? And in the graph on the bottom right, that function is going to remain linear because it's of the form y equal to beta 0 plus beta 1 times w. And so the goal is to modify these coefficients in stepwise fashion to see if we can visually get these functions in green to correspond to more closely to the data points. And when we get close, we're going to be keeping an eye on the values of SSE that we have in both tables. Now, one thing I want you to pay attention to is the values of SSE in those two tables and see if they remain the same. Again, we're fitting different models, at least notationally, in these two models. And so we want to see, does that, what happens to SSE? But the bottom line is we're going to see if we can tweak these parameter estimates to get the minimum possible SSE. And if we can, that will be the best fitting function according to the least squares criterion. So let's start off by, I think what I'll do is start off with the slope or the intercept coefficient, and I'm going to decrease that a bit and get it to a point closer to where we think it needs to be, so maybe about there. All right. And then I'm going to adjust the parameter estimate beta 1, and that's going to be multiplied against x squared in the graph on the left and multiplied against w, all right, in the graph on the right. And so let me start to increase that. Okay, and you can see in the graph on the right that the function is linear, and it's becoming closer and closer to the trend of the data points, which, again, the scatter plot on the right-hand side is linear. And if you look at the graph on the left, as we have increased that coefficient, then we're seeing curvature in that graph. So this is a quadratic function that we're fitting to this scatter plot that has this quadratic trend. And so it looks like we're getting fairly close. Let's see what happens if we modify these two parameters a bit. And so the SSE in both tables is currently 0.3362. Okay, and so increasing beta 1 hat decrease the SSE. And so let's see if we increase it a little bit more. Well, okay, so SSE increased. And so let's keep beta 1 hat at 5.3 for now. And now let's see what happens if we lower beta 0. Okay, so by lowering it, SSE increased pretty dramatically. And so let's increase it a little bit from 2.4 up to 2.5. Okay, so that increased SSE. Okay, what I'm going to do next is I'm going to change the resolution a little bit on each of these parameters. so that we can fine tune it just a little bit more. And so instead of changing in increments of 0.1, I've changed it to increments of 0.01. And so we should be able to get a little bit finer resolution. Okay, and so increasing it beta 0 to 2.41 from 2.4 decreased the SSE a little bit. Let's see if we can continue to decrease it. Okay, so it looks like 2.44 was where we need to stop for that. Let's see what happens. Okay, if I increase beta 1, then SSE goes up. If I decrease beta 1 a little bit, okay, it is decreasing. Okay, we're going in the right direction. Okay, it's still decreasing. Okay, let me see if I decrease beta 0 a little bit. Okay, that increased it. Okay, increasing beta 0 hat is decreasing SSE a little bit. Okay, let me try beta 1 hat again. Okay, that decreased SSE. Okay, so you can see that this is kind of a tedious process. Let's do it just a little bit more. We won't spend much more time on this. Okay, so let's stop there. We can fit this quadratic curve very, very closely, or this quadratic trend very closely, using this visual technique that we applied originally to a linear trend. And we can get very close to what would appear to be the least squares estimators, and the SSE appears to be fairly close to 0.2755. Now, if we had more time and increase the resolution of the adjustment cells here, we could perhaps get a little bit closer, but this is close enough for the purposes of this visual demonstration. You can see here by tweaking the parameter estimates and appealing to the least squares criterion, we can in fact fit a curve, a quadratic curve, to a curvilinear data set. And when we do that, the sum of squares error for that curve is identical to the sum of squares error that we would get if we were to use, instead of x as the explanatory variable, x squared as the explanatory variable. Okay, next, let's find the least squares estimators of this quadratic relationship by solving the normal equations. And so let's take a look at what the normal equations for the quadratic simple linear regression model look like. We want to fit the following model to the data. Y equal to beta 0 plus beta 1 times x squared plus epsilon. This can be re-expressed in canonical form as y equal to beta 0 plus beta 1 times w plus epsilon. In the first representation, the deterministic part of the model is quadratic in x. In the second representation, the deterministic part is linear in w, or equivalently linear in x squared. But both of these models are linear models because they are linear in the parameters beta 0 and beta 1. Remember that this is the defining characteristic of a linear model. Since there is only one explanatory variable in each representation, x squared in the first representation and w in the second, each is a simple linear regression model. We can therefore use techniques for simple linear regression to fit this model. The important thing to remember in fitting the model is that we will not be regressing y on x. Rather, we will be regressing y on x squared. The normal equations associated with the canonical form of the simple linear regression model, that is, the version expressed in terms of w, are shown on the bottom of the slide here, and they involve the sum of the w's, the sum of the squared w's. And this looks similar to the versions of the normal equations when we used x as the explanatory variable in previous development. On the other hand, the normal equations associated with the version of the simple linear regression model expressed in terms of x squared, so y equal to beta 0 plus beta 1 times x squared plus epsilon, look a little different. Notice that instead of, in the first line, having beta 1 hat times the sum of the x's, we have beta 1 hat times the sum of the x squared values. And that's because x squared is equal to w. All right, and so we need to replace w with x squared because w is equal to x squared, and that same type of thing happens in the second row. For example, look at the term involving beta 1 hat there. Beta 1 hat times the sum not of the squared x values, but of the x's raised to the fourth power. And then finally, on the right-hand side of that second equation, instead of the sum of the x's times the y's, we have the sum of the x squareds times the y's. So we get these formulas by looking at the previous representation, all right, where we have the w's, and these normal equations are expressed in canonical form, but we replace each w by x squared. The two sets of normal equations differ only in the notation used for the explanatory variable. The numerical values of the summary statistics will be the same. Therefore, either representation of the normal equations can be used to find the least squares estimators of beta 0 and beta 1 in the simple linear regression model, y equal to beta 0 plus beta 1 times w plus epsilon, which is equivalent to the model beta 0 plus beta 1 times x squared plus epsilon. The least squares estimators beta 0 hat and beta 1 hat that we find will satisfy both sets of normal equations. So here are the summary statistics needed for the normal equations, expressed using both sets of notation, that is, expressed both in terms of w and also in terms of x. So the sample size is 10. The sum of the w values, which is equal to the sum of the squared x values, is 3.84. The sum of the squared w values, which is equal to the sum of the x values raised to the fourth power, is 2.5332. The sum of the response variable y is 44.74, and the sum of the products of the w and y values, which is equal to the sum of the products of the squared x values with the y values, is 22.6249. Substituting these summary statistics into the normal equations for this model gives the following system of equations. So the first equation is beta 0 hat times 10 plus beta 1 hat times 3.84, and that sum must be equal to 44.74. The second equation is beta 0 hat times 3.84 plus beta 1 hat times 2.5332, and that sum must be equal to 22.6249. The least squares estimators, beta 0 hat and beta 1 hat, are the solutions of this system of equations. The augmented matrix for this system of equations is given by this 2x3 matrix, the entries corresponding to the coefficients and constant terms in the normal equations themselves. The first row has values that come from the first equation in the normal equations. Those values are 10, 3.84, and 44.74. The second row has entries 3.84, 2.5332, and 22.6249. 6249, and these values come from the second equation in the normal equations. We will apply Gaussian elimination with Jordan reduction to this matrix to obtain the augmented matrix of an equivalent system of equations that is going to be much, much easier to solve. Now, again, when we say equivalent, what we mean is that the reduced matrix that we obtain will have the same solution set. And so the solution of the reduced matrix will be the same as the solution of the original system, which are the normal equations. The resulting solution will therefore be the least squares estimators, beta 0 hat and beta 1 hat. So we're going to solve the normal equations via Gaussian elimination with Jordan reduction, and we're going to do it on the TI-84 calculator as we did in a previous lecture. And so let's take a look at that. So we're going to fit a quadratic trend using a simple linear regression model. We'll fit the model using the least squares criterion, and we'll find the least squares estimators by solving the normal equations. We'll solve the normal equations by applying Gaussian elimination with Jordan reduction to the augmented matrix for that system. One thing we need to keep in mind is that in doing this, we're going to be regressing the response variable y not on x itself, but on w equal to x squared. So we need to keep that in mind as we go forward. Now, the first thing we need to do is to make sure that we have the data in the calculator and that the data is set up correctly. And so let me go over here to Stat and enter the list page. And so you can see here that I've already got the data entered into the calculator. List 1 contains the explanatory variable x, and list 2 contains the values for the response variable y. Now let me go ahead and bring up the list in this right panel. Now the data set is not set up quite like we need it, because remember, we're going to be regressing y on x squared, which we're calling w, not regressing y on x itself. And so what I need to do is I need to get the squared values of x in a list. And so what I think I'll do is I'm going to move the values in list 2, which are the values for the response variable. I'm going to move those over to list 3. And then I'm going to calculate the squared values of the values in list 1 and put those in list 2. All right, and so let me quit out of here. And the first thing I need to do is save the values that are currently in list 2, which are the values of the response. I need to save those in list 3. And so this is how I'm going to do that. All right, and so you can see here that I've copied the values from list 2 into list 3. So I preserve those values. And then what we're going to do is we're going to square the values in list 1 and put those in list 2. And so I'm going to have the actual explanatory variable that I'm going to be regressing on, x squared, again, which we're calling w, in the second column. And so that, again, is something that we're going to need to keep in mind as we go forward. As we go processing this data, the response variable is now in list 3, and the actual explanatory variable we're using, w, which is x squared, is in list 2. So let me go ahead and square the values in list 1 and store those in list 2. Let me refresh. And so now you can see that we have the squared values of list 1 in list 2. Okay, so let me clear out the key press history. And what I'm going to do next is let's create scatter plots of our data. And I want to create two scatter plots. I want to have a scatter plot of the response variable y versus x, so list 3 versus list 1. because I want to be able to see that curvature in the data. But then we're also going to create a scatter plot of of y versus x squared, so list 3 versus list 2. So we're going to have two scatter plots. Let me go up here, and for plot 1, let's use this one to plot y versus x itself. And so the plot is on. Scatter plot type is selected. The variable for the horizontal axis, I want to keep that at list 1, that's x, but the response is going to be list 3. That's where the y variable is, and so I need to select list 3. Okay, and then I can press the zoom button and then select zoom stat, which is option number 9, and that's going to size the window correctly. All right, and so here we have the graph of y versus x. And actually, I'm probably not going to be able to display both at the same time. And so what I'm going to do, I'm going to leave this plot here. We'll be doing the calculations with list 2, but for display purposes, I want to keep y versus list 1, or y versus x in the plot. All right, so let me clear out the display, and I'll again clear out the key press history. Okay, so the next thing we need to do is to calculate the summary statistics that we're going to be using to create the augmented matrix for the model that we're going to be fitting. And remember, we're regressing y against w, y against x squared, rather than y against x. And so we need to keep that in mind here. And so I'm going to press the stat key to enter the stat menu, and then arrow over to the calc menu. We're going to select two variable statistics. And then the x list, all right, we can think of this as the explanatory variable list, is not going to be list 1, that's going to be list 2. And then the y list, we can think of that as the response variable list, that is now in list 3. Okay. And we press enter. And here we have the summary statistics that we'll be using. And so even though this says x, we know in the back of our mind that really we're representing that as w. All right, so we have the summary statistics for list 2 here at the top. And then if we scroll down, we have the summary statistics for the response variable, which is in list 3. Okay, so the statistical registers have been populated with these summary statistics. And so let me clear the screen and clear the key press history. And I think what we'll do is, do we want these? Let's see. No, we don't need anything else there right now. Okay, so the next thing we need to do is we need to calculate or create the augmented matrix for the, or associated with the normal equations for the analysis for the model. And so we're going to press the second key and then go to our matrix menu. And you can see here that none of these matrix variables have dimensions next to them, so none have been defined yet. And so we need to go over to the Edit menu and select one of these matrix variables. Let's just select matrix A. Because this is a simple linear regression with one explanatory variable, two parameters, beta 0, beta 1, the augmented matrix for the system is going to be a 2 by 3 matrix. And so we enter the dimensions here. Okay. Okay, and then the first row in this augmented matrix corresponds to the first row in the normal equations, and the first row in the normal equations, the first equation in the normal equations, is beta 0 hat times n plus beta 1 hat times the sum of the w's plus, or that's equal to, on the right-hand side, the sum of the y's. And so that is, those are the values that we need to put in this first row. N, the sum of the w's, and the sum of the y's. And we get those values from the statistical memory locations. So I'm going to press my vars key and then toggle down to statistics. Press enter. All right, and the first entry we need is the sample size, and so that is 10. The next value in row 1 is the sum of the w's, and so again go to vars, 5, sum. Okay, and remember that this represents the sum of the w's, and so I'll select that, and that's equal to 3.84. And the last entry in row 1 corresponds to the sum of the response variable, so the sum of the y's, and so vars, statistics, sum, and then the sum of the y's, so option 3. And that's 44.74. Okay, the second row in this matrix corresponds to the second equation in the normal equations. The second equation of the normal equations is given by beta 0 hat times the sum of the w's plus beta 1 hat times the sum of the squared w values. And that sum is equal to the sum of the products of the w's and the y's. And so those are the values that we need to plug in here. All right, and so the first entry is the sum of the w's. So I go to vars, statistics, sum, and then again that's the sum of the w's right there. So that's going to be 3.84 as it was up there. This entry is the sum of the squared w's, and so vars, statistics, sum, and then option 2 here. And so that's 2.5332. And the last entry in row 2 is the sum of the products of the w's and the y's. Okay, and so that's vars, statistics, sum, and then option 5. Okay, so 22.6249, and it rounds it to 22.625. Okay, so we have constructed the augmented matrix for the normal equations for the canonical form of the model, which is y equal to beta 0 plus beta 1 times w plus epsilon. Okay, so we can quit out of that. And if we wanted to, we could just print out that matrix just to verify, take another look at it. So that looks fine. Okay, let me clear out the key press history again. And now what we want to do is we want to apply Gaussian elimination with Jordan reduction to this matrix. We do this, let me just say parenthetically here, we're wanting the solution to the system represented by this augmented matrix. But we can't get that solution just by looking visually at this augmented matrix. At least I can't. Maybe you can. Okay, maybe you can solve this system, okay, just by looking at it, but I can't. I need a much simpler matrix to solve. All right? And so when we apply Gaussian elimination with Jordan reduction to a matrix like this, we get a matrix that's in reduced row echelon form that's easy to solve. I can just look at that matrix and solve the system, and it's an equivalent matrix, and what that means is that it has the same solution set as the original matrix, as the original normal equations. And so that's why we're doing this. So to access that function, which is the RREF function for reduced row echelon form, we press the second key, get back into our matrix menu, and then we want to do math on a matrix. And so we want to invoke the RREF function, and we want to apply that to the A matrix. Right? So I'm just going to grab that and copy and paste it into the argument list there. And when I apply that, I get an equivalent matrix to the original. This matrix is in reduced row echelon form. Again, the 1 here in the first row, that is the coefficient on beta 0 hat. The 0 in the first row is the coefficient on beta 1 hat. And the entry here on the in the third column in the first row is the value on the right-hand side of the equation. And so that first equation is beta 0 hat equal to 2.499031,966. So we have the solution for beta 0 hat given by that first line. In the second row, the 0 is the coefficient on beta 0 hat. The 1 is the coefficient on beta 1 hat. And the entry here in the third column is the constant on the right-hand side of that equation. And so what that equation says is that beta 1 hat is equal to 5.143145923. And so that gives us the least squares estimators, or the solution of the normal equations, which are the least squares estimators of beta 0 and beta 1 in that canonical form of the simple linear regression model. And because that canonical form, y equal to beta 0 plus beta 1 times w plus epsilon, is equivalent to the model expressed in terms of x squared. So y equal to beta 0 plus beta 1 times x squared plus epsilon. Okay, these are the least squares estimates for that model as well. Okay, so what I want to do next is to plot the estimated regression curve in this case and superimpose that over the scatter plot. And so now what we're going to do is we're going to go back up into our function key, y equal to key, and we're going to enter the estimated regression equation. But we have to be, because the plot here is plotted in terms of x instead of w, we need to make sure to express this estimated model in terms of x squared. Okay, so let's do that. Actually, before I do this, hold on a second. I've got to go back here. I've got to save this to a matrix so that I can reference these values. And so let me save that to matrix B. All right. Okay, you were going to let me forget that, weren't you? Okay, so let me clear this out. And let me just remind you how we can access those particular entries. So we want the beta 0 hat value. Okay, we want to extract that from the matrix. And so we're going to select matrix B. And then we're going to type in a left parenthesis. And the entry we want is in row 1, column 3. Okay, so the 2.499. And then we want the value for beta 1 hat. Okay, I'm just going to copy and paste this down into the command line, and then I'm going to arrow over and change row 1 to row 2. And so there we have beta 1 hat. So that's the kind of thing we're going to do as we express or define this function that we're going to plot. So again, I go to second and then matrix. All right, matrix B. The entry we want for beta 0 hat is in row 1, column 3. To that, we're going to add beta 1 hat times x squared. Okay, so beta 1 hat is, all right, the entry in matrix B that's in row 2, column 3. And that's multiplied. And again, we're superimposing over this plot that has x on the horizontal axis. Okay, and we need x squared here, okay, because in that model where x is on the horizontal axis, the model we're actually fitting is y equal to beta 0 plus beta 1 times x squared plus epsilon. Okay, so let me press enter here. Okay, and let's go ahead and graph that. And so you can see that that's the least squares least squares regression curve for this quadratic model. So it's a linear model in terms of the betas, but in terms of x, okay, this is a quadratic model. Okay, so that is how we can plot that. Let me quit out of that and let me clear the screen and clear the key press history. Okay, the last thing I want to do is calculate the sum of squares error for this predicted model. And so what we need to do is to calculate the predicted values of y. And so let me arrow back up here. You'll recall that the predicted value of y hat, is equal to beta 0 hat plus beta 1 hat times each x value in the data set. And so I've already got beta 0 hat and beta 1 hat extracted from the matrix, so I can just arrow up and copy and paste those down into my command line. So beta 0 hat plus beta 1 hat times, okay, here we have to be careful again because, well, we just need to, if we're going to use x, or list 1 as the explanatory variable for this purpose, then we need to be sure to square those values. If we're going to use the values in list 2, that is w, and we would just leave those as is. So you just need to be sure of what you're doing here. And so let's multiply that against the values in list 2, because that's already, that has automatically squared the x values. And let's calculate, let's press the enter key, and that's going to produce a list with the predicted values. Now I'm going to store those predicted values in list 4. So store and list 4. There they are. Okay, and then what we're going to do is we're going to take the difference between the values in list 3, which are the observed values of the response, subtract from those the predicted values of the response, and we're going to square those differences. All right, and so I'm going to type in a left parenthesis, and then select list 3. From the values in list 3, I'm going to subtract the corresponding values in list 4. I'm going to square those values, and I'm going to store those squared differences in list 5. Okay. And then finally, to get the sum of squares error for this least squares line, I'm going to add up the values in list 5. And so I go to second and then list. I want to do some math on a list. And in particular, I want to sum up the values in a list, the values in list 5. And so we get the value of SSE for this least squares curve equal to 0.27314766668. So we have used the TI-84 to perform Gaussian elimination with Jordan reduction on the augmented matrix corresponding to the normal equations, converting it to reduced row echelon form. The reduced matrix is the augmented matrix for the system of equations given at the bottom of the slide, which is equivalent to the original system of equations, that is the normal equations, and therefore has the same solution set. The solution to this reduced system can be read directly from the reduced matrix. And so we see that beta 0 hat is equal to 2.499,031,966, and beta 1 hat is equal to 5.14,314,5923. The least squares estimators of beta 0 and beta 1 are therefore beta 0 hat equal to 2.499,031,966 and beta 1 hat equal to 5.143,145,923. The least squares estimate of the simple linear regression model is given by y hat equal to beta 0 hat plus beta 1 hat times w, which is 2.499,031,966 plus 5.143,145,923 times w, and we can also express this in terms of x as y hat equal to beta 0 plus beta 1 times x squared, which would be 2.499,031,966 plus 5.143,145,923 times x squared.